All right, good morning. Special shout out to the class of 2022 making this video just for you guys. Actually, I just didn't have a good video of this in my library, so that's why you guys are getting it. So starting chapter 4 today, unfortunately we're having to start it this way. We're still going to be doing a lot of differentiation, but today we're starting this unit, we're going to be doing applications of differentiation. So a lot of word problems, graphing. How are we going to use differentiation to maybe make some of the algebra that we've learned easier, to make some of the graphing that we've done easier? So we'll be looking at all of that this chapter. Specifically in this video, we're going to be looking at maximum minimum values. We did these in Algebra 2. We did these in Pre-Calc A last year. This is just where I'm looking for the little hills and valleys of a graph. We used negative b over 2a to find maxes and mins, and those were relative maxes and relative mins on a parabola. But calculus is going to help us do this a little bit better today. So whenever we're finding maxes and mins, we're looking at optimizing problems. All right, we're finding the best way of doing something. We're finding the most profit that we can get. We're looking at anyway, just I guess what I said, the best way of doing something. So finding the max or min of a function will help me get there the quickest. And so I'm going to let c be a number in the domain D of a function. Then f of c is going to be known as the absolute minimum. Let me make sure here I'm on the right one. Yes. Absolute minimum value of f on D if f of c is greater than f of x for all of c for all of x in D. That seems backwards to me. Of course it is, right? So did this backwards. Could start the video over here, but we're just going to go with it. Excuse me. Okay, so I'm just going to draw just a regular graph down here. I'm going to try to hit some different points on this. I'm going to actually bring that back down right there. And so when we're talking about the absolute maximum, I'm talking about the absolute highest point on a graph. And so the absolute maximum would be this red dot right here. Okay, and so this would be the point C that I'm talking about. And according to this definition, what it means is that f of c, this point right here, is higher than all the points around it. That's all we're looking at on this definition of absolute maximum. Absolute minimum is going to happen all the way back here. Absolute minimum is going to be the absolute lowest point on the graph that is given. And so I use C again, it won't be C, but the idea is that this is the lowest point, the absolute lowest point on the graph. Now there's another type of max and min values that we're going to be interested in called local max. I didn't leave myself as much room to write those. So I'm guessing it's going to go local max, local maximum, and local minimum. Okay, now minimum, it can be the highest, it can be the lowest value that I have. It doesn't have to be. The idea of the local maximum is that it's just higher than all the values close to the point right here. That looks like a good local maximum to me because it's higher than all the points around it. If you're thinking, wow, it's just where it forms a hill, you're exactly right. Because this red dot, it's also going to be, not only is it an absolute maximum, it's also going to be a local maximum as well. Whereas the local minimum, it's going to be kind of weird. Local minimum, they're only going to have one local minimum on here. It's going to be right here where this black dot is. That is my local minimum. it is smaller than all the points around it. So it has to be points on either side that it's smaller than in order for it to be local. Okay, this blue dot down here, not a local minimum since I don't have the points on the other side. So that's how your homework will start off. I think it's just going to give you a graph and ask you about maxes and mins. We could definitely do this, though, with some graphs that we already know. For instance, cosine. Oddly enough, as soon as this video is done, I'm getting ready to make a video for Pre-Cal B on how to graph sine and cosine. And remember, cosine is going to be the wavy lines that go from 1 to -1. And it starts on the hill. And it's saying find the max and min values. If it's not being specific as to which max and min values to find, I would just find both local and absolute. Well, looking at this, all the local maxes are going to be the same as the absolute maxes. All of these will be local and absolute maxes. So I could just say local and absolute maxes at, and I'd like for you to get 2 pieces of information on this. Okay, I'd like for you to tell me the x value, which it happens, which is going to be, let's see, this is going to be 0. I completed a full cycle. This is going to be 2 pi. Complete a full cycle. It's going to be 4 pi. So every even multiple of pi. So cosine of 2m pi. And tell me what the value is. The value is going to be how tall these little hills are. Well, each of the little hills come up to 1. So to get my local and absolute min values, those are going to happen at, well, all these little valleys down here. So I see that they're all going to have a value of -1, but where do those little valleys occur? Well, halfway between all the even pi's. So every odd multiple of pi. A couple ways you can write it. The most prevalent one you see is 2n plus 1 pi. The idea is if I plug in any number in for n on either this red one up here or the blue one, this red one I'm always going to get an even number, and the blue one down here I'm always going to get an odd number for pi. Now luckily you won't have to do this just with trig functions. Okay, we'll do some with just some basic parent functions as well that we've been reviewing. Okay, so I'm actually going to pause the video, let you work this one. Tell me about the absolute max, local max, absolute min, local min of this function. So hit pause, I'll work the problem while you do, and then we'll come back. I hope I'm back rolling again. I accidentally hit stop instead of, oh, well, let's go with it. I'll check it later. All right, so hopefully we get this. Functions do not have to have a max or a min value. Okay, if it does not form a hill or a valley, there's no local maxes, local mins. And if we're going all the way up to infinity, like we are on x squared right here, we won't have any. All right, good. X cubes are a great example of something that will have neither a max nor a min. Remember, x cubed just going to be my snake on a plane. There's a little spot right here that's kind of questionable, but it doesn't form a hill or a valley right there. So no local max, no local min. There's not an absolute highest point because it goes to infinity. There's not an absolute lowest point because it goes to negative infinity. So no local maxes or no maxes or mins on that. Okay, so this brings me to a very important theorem known as the extreme value theorem. The extreme value theorem, if I am on a closed interval from A to B, then f attains an absolute maximum value and an absolute minimum value, f of d, at some number c and d in AB. What does that mean? Let's draw it out. It means that if I am going from, say, A right here to B right here, and I connect them however I feel the best way to connect them is. What this extreme value theorem says is that if at some point in between these two, there has to be an absolute maximum right here at C and an absolute minimum right here at D. Let's try to debunk it. That'll be fun. So what if my A to B looks like this? What if I don't put a little valley in there? I think I've got it, right? So I'm going from A to B. I've messed it up because look, I've only got a C right there. So definitely need to call all my calculus friends, there's a lot of them, and let them know that I just disproved the extreme value theorem. But wait, it just says it has to have an absolute min value. An absolute min value just says that there has to be some point that is the lowest point, and that happened right there at point A. So A and D are sharing that point at the end. What if I throw it off? I'll just do this number. Let's act like that didn't happen. Oh, I did it again. We're going to get it. We're going to get it. Talk amongst your friends while I get this right. Oh, I think that's good. I think that's good. So, trying to throw it off here. I'm going to go from A to B. And I see my min value. My min value happened right here at D, down at the bottom. But which one's going to be my max? Well, it just says it has to attain an absolute max value. It didn't say that it has to be just one. It just says there's gonna be a max value, and they're right. There's gonna be a max value here and here. It doesn't say there has to be one. It just says there's gonna be a max, and there happens to be two on this one. So that's perfectly fine. All right, I'm gonna throw them off. All right, what if I just right there, and then I come down to here. Yeah, I think I've got them. A to B. So, I see this is probably my lowest point right here. So that's going to be my min value, my D. But the max value, problem is the max is going up, 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 and then all of a sudden it comes back down. I mean, which one's going to be the max value? Am I going to look at this one? Am I going to look here? Which one's going to be the max value? And the answer is this one does not have a max value. So I need to get my calculus friends back on the phone. I need to let them know I just debunked the extreme value theorem. Oh, you know what though? They said it had to be continuous in order for this to work. I have a jump discontinuity going from here to here. So that one's not going to fall in for it. All right. So make sure you're meeting all of the requirements on this extreme value theorem if you're going to be using it. All right. All right. That's enough of that because I think we're ready for Fermat's theorem. Fermat said that we're going to have a local max or local min at C if, check this out. The derivative of C, if that exists, then f prime of C equals 0.
At this time, student 2 ate lunch A should return to class. Student 2 ate lunch A should return to class.
So let's go back and draw our fun graph here. So Fermat says that if I have a local max or local min, okay, so let me find my local maxes. let's see, local max and local min. Okay. He said that if I have that local max or local min on my graph, then what happens if I take the derivative there, then the derivative has to equal 0. Well, think about what we know about derivative in graphs. It means that the slope of the tangent line is 0. Are the slopes of the tangent line here 0? Yes. We've been kind of working problems like this. So this is just going to be where I have a horizontal tangent line. That's all Fermat is saying on this. This is definitely proved in your book using left and right hand limits. And so it's pretty neat how it works. I'm going to skip that because I'm trying to really cut down on the length of this video. So now, let's try to work a problem from earlier in the video where I'm trying to find the extreme values of x cubed. Well, I'm just going to try to throw off Fermat's theorem, actually. Because look, if I do f prime, that's going to give me 3x squared. And Fermat said that wherever this is equal to 0 at 0, I should have an absolute max or absolute min. So let's get my calc friends back on the phone. I just disproved Fermat's theorem, however long that's been out there, because I just found where the derivative is at 0 on this x cubed function. We said earlier that it was just a snake on a plane. And there's not a max or min anywhere, especially at 0. Kind of levels off for a little bit. Oh, wait, you know what? Fermat didn't say that. Fermat said the opposite of that. He says if you have a local max or local minimum, if there is a local max or local minimum, then the derivative will be 0 there. Not where the derivative is 0, then there has to be a local max or local min. So the converse of Fermat's theorem is not going to be true. I didn't disprove it. I'll keep trying though. Okay, let's look at the extreme values of the absolute value of x. Remember, the derivative of this gets kind of weird. We have to do like a whole piecewise function on it. And it's equal to 1 if x is greater than or equal to 0. It's equal to -1 if x is less than 0. We've proved that before. We've shown it. And that's how we get this v right here. So look, I have a local min right here, right? I have a local min, but f prime of 0 is not, f prime of 0 is not defined. Or f prime of 0 does not exist. Because it gives me a sharp corner, a kink. I'm not allowed to have sharp corners there. So, did I just prove it? Maybe we just need a better definition of it. Okay, so let's hang on to that one, and then we'll come back to that and try to get a better definition for what's going on there. Because actually what we're going to be doing is we're going to be looking for critical numbers. If I'm looking to find max and min values, the best way to do that is going to be to use something called a critical number. And a critical number is just a number that's that is in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. So just like on those last two examples I worked, I'm looking to see where the derivative is equal to 0 or the derivative does not exist. So if I'm just looking for critical numbers of this function, then I just want to find the derivative of it and set it equal to 0. I'm going to let you practice finding the derivative of it. All right? So let's hit pause on the video. I'm going to let you find the derivative of it, and then I'll find the derivative, and we'll see if we work it the same way. And then we'll find the critical numbers together. All right, hit the record button this time. So should be good. I found this derivative two ways. I did the blue way over here on the left is going to be my product rule. I did a nasty product rule with it. Cleanup on it was kind of tough. Tried to make it so it was one fraction. You'll see why in just a minute. The red way, I was trying to avoid the product rule. So I distributed it x to the 3/5, and then I just had a simple power rule. And then again, I got to get a common denominator so I can subtract these fractions. And that was the best I could do. All right, so either way you want to work, it's fine. I'm going to keep the blue way because it was over on the left. And so whenever I'm looking at a critical number, I'm interested in what makes it equal to 0. Well, when I'm dealing with a fraction, so what makes a fraction equal to 0 is going to be whatever makes the numerator equal to 0. Or you can just think about it. If I set this derivative equal to 0 and I multiply both sides by 5x to the 2/5, I get exactly this. So either way you want to think of it. And then from there, I just have it add 8x, divide by 8. X is going to be 3/2. That's going to be one of the critical numbers. I'm going to be able to get another critical number because anything that makes my derivative down here undefined. Well, what makes a fraction undefined? The bottom equaling 0. So if I do 5x to the 2/5 equals 0, divide by 5, anything in 0 power is going to be, or 0 raised to any power is going to be 0. So I end up with two critical numbers on here. Okay. So why do I need critical numbers? Let's look and see. The critical numbers are going to help me with something called the closed interval method. Okay. And if f is going to have a local max or local min, then it's going to happen at a critical number. Notice I didn't say that if it's a critical number, it's going to be a local max or local min. I'm saying if it's a local max or local min, it's going to come from one of these critical numbers. So here's my closed interval method, a little three-step process. I want to make sure it's continuous and closed. That's not going to be an issue. I know I tried to throw you off on that earlier. It's not going to be an issue on this. So I want to find the values of f at the critical numbers a and b. So I'm looking at finding my critical numbers first, and then I'm going to plug them back in, and I'm going to get some function values for it. And then since it's a closed interval method, I should be given a closed interval. I want to find the values of the endpoints on my interval. In steps 1 and 2, between those two steps, I'm going to look for the largest value I have. The largest value I have is going to be known as the absolute max. I label it as such. And then I'll look between all the numbers I got between steps 1 and 2. I'm going to look for the lowest number that was given to me. When I find that lowest number, I'm going to call that my absolute minimum value. So this doesn't help out a lot with local maxes, local mins. Some of these will be local maxes, local mins, but they're going to really help me find absolute maxes and absolute mins. So I'm wanting the absolute max and min of this. And the big giveaway that makes me know I'm going to use the closed interval method is that, you guessed it, I was giving a closed interval. So first up, I need to do my f prime. Okay, when doing my f prime, what I'm going to do is take my derivative. It's going to be simply 3x squared minus 6x. And I need to find my critical numbers. So to find my critical numbers, I'm going to set this equal to 0. Sin equals 0, I just have a simple factoring here. I see they both have a 3 in common, they both have an x in common. So I pull out that 3x, I get 3x equals 0, which is just x equals 0. And I get x minus 2 equals 0, which just gives me x equals 2. So what I'm going to do is I'm going to make myself a little list over here of all my critical numbers. Something's happening at f of 0, something's happening at f of 2. Now, since I'm using the closed interval method, what I'm going to do is I'm going to bring down this negative 1/2. He's going to get in on the game. And I'm going to bring down this 4. She's going to get in on this game. Kind of goes back to the very first thing that we drew in the notes when we had my absolute minimum was on my endpoint, on that f of a. So now, I'm going to take all these values, 0, 2, negative 1/2, and 4, and I'm going to plug it in for these x's. Because remember, I'm actually trying to find absolute max, absolute min of this function right here. My derivative is helping me do that, but the goal is to work with this function. So when I plug in 0, I got 1. When I plugged in 2, I get negative 3. I plug in negative 1/2, that gives me 1/8. I plug in f of 4, that gives me 17. Now what we're doing is looking for a winner and loser. A winner is going to be whoever has the highest value. Right here, there's my winner. I'm going to call this my absolute max. Looking for a loser. Loser is going to be the one that has the lowest value. Ooh, I went down to the negatives. This would be my absolute min. So this is using calculus to find absolute maxes, absolute mins. We got to find that derivative, do the critical numbers, and then plug everything in to see who wins and who loses. All right, your turn. I'm going to give you one that has some trig in it. I know how much you guys like trig, especially the class of 2022. So we're going to hit pause again. The last time we hit pause, and then I'm going to work it while you work it. So we're going to do a derivative, find the critical numbers, and then plug in everything. Calculator should be in radians on this if you're going to be using a calculator. I'll see you guys in a few minutes. Using my table feature on my calculator really expedites this process if you can work through that. If not, definitely ask me about that in class, and I'll be glad to show you. So only ended up with one negative number. So I'm just going to put a little absolute minimum over here. That's gonna show the teacher that I know that's my absolute minimum. And my absolute maximum ended up at this 2 pi right here. And that would be full credit. Okay. Okay, let's work one more. Where would we use this closed interval method at in the real world? Well, back in 1990, when the Hubble Space Telescope was deployed by the Space Shuttle Discovery is when it was used. And so a model for the velocity of the shuttle during this mission from liftoff until it got rid of its rocket boosters is given by this V of t right here in the middle of the screen. So using this model, I want to estimate the absolute maximum and minimum values of the acceleration. That's going to be a kicker right there, of the shuttle between liftoff and whenever it got rid of its boosters. So I see that I'm going to be using a closed interval method. At liftoff, we're looking at time equals 0. And whenever it got rid of its boosters, we're looking at 126 seconds. Now, I'm looking for maximum and minimum values of the acceleration. Let's go back real quick. I was looking for maximum and minimum values of this function right here. All right. So if I'm looking for maximum and minimum values of acceleration, that means I'm going to need an acceleration formula, which I'm going to get from just taking the derivative of velocity. If I take my derivative of the velocity, I'm going to do 3 times this. It's got a simple power rule here. 0.003906. And then lower the exponent by 1. Minus 0.18058 t plus 23.61. That would be an equation for my acceleration. Now, if I'm wanting the maximum minimum acceleration, I'm going to have to find critical numbers of this guy, which is going to mean I need the derivative of him. So I actually used two derivatives on here to get to where I needed to be in the problem. When I find the derivative of a of t, let's see, and multiply that down, that's going to give me 0.007812. And just get rid of the t here. So it would be 0.18058. And so I need to find the critical numbers of this. So whenever I set this equal to 0, let's see, that's going to be 0.007812t equals 0.18058. Divide that off. We're just going to go decimal on this. That's going to make more sense. 23.12 seconds. That's really bad. C, seconds. That's going to be my critical number. Something might have happened at 23.12 seconds to make it so the acceleration was at a maximum or minimum. I'm going to use my closed interval method to find out. So I need to go back to my acceleration equation, and I'm going to plug in 0. That's when the rocket took off. When the rocket took off, if I plug in 0 right there, I see the rocket is going 23.61. Do we have a unit on that? Feet per second. Okay. I'm going to plug in my, I'm just kind of going in order from biggest to smallest. I'm going to plug in my 23.12 seconds in for these t's, here and here. And that gave me 21.52. Ooh, so it slowed down. Okay. And then whenever I got rid of its boosters at 126 seconds, it was booking it. It was going 62.87 feet per second. So that means that this would be my absolute max whenever the acceleration was at its quickest. And this critical number I found right here, the 23.12, this would be its absolute minimum when the acceleration was at its minimum. A lot going on there. I skipped some of the calculator problems. They're not going to be too hard to show on the homework day. This should be the assignment. Make sure you check in Google Classroom to make it so that it matches the current year that you're in. And so good luck with it. If you have any questions, let me know. If I made any mistakes on this video, make a comment, and I'll definitely get that cleared up. Hope you guys have a great day, and we'll see you next time.